Hello there, and welcome to the Sleepy Science Story. We can measure stars, map galaxies, and trace time back to the Big Bang, yet the deepest questions remain unanswered. What sparked the beginning of everything, and what unseen forces shape reality right now? From invisible matter holding galaxies together to energy stretching space itself, most of the universe is still a mystery. Tonight isn't about facts you already know, it's about the questions science can't yet explain. So get comfortable, slow your thoughts, and let curiosity guide you into the unknown. Let's begin. One of the deepest mysteries of all remains unanswered. Why does the universe exist at all? It seems like the simplest question, yet science offers no definite answer. Physics can explain how the universe behaves once it exists, and cosmology can trace events back to the Big Bang. But why there is a universe in the first place, and why it follows the laws it does, is still unknown. Quantum physics hints that nothing may not be truly empty. Even the vacuum of space is alive with fleeting particles that appear and vanish in an instant. Some scientists propose that the universe itself might have emerged in a similar way, that true nothingness is unstable and something must inevitably come into being. Some scientists suggest that our universe may be just one among countless others in a vast multiverse, each emerging with its own distinct laws. But if that is true, it only pushes the mystery further. Why does the multiverse exist at all? Philosophers have proposed that existence itself may be the natural state, that non-existence is impossible, that reality in some form must always be. Yet these ideas remain beyond our ability to test. No telescope, no particle collider can reveal why there is something rather than nothing. Every question in science, every law of nature, every star in the sky, and every atom in your body rests on this unfathomable foundation. The very fact that reality exists at all is the deepest mystery we face. We can trace the story of the cosmos nearly 14 billion years back to a time when the universe was an unimaginably hot, dense fireball, the event we call the Big Bang. But what triggered it? That too remains unknown. Cosmologists have reconstructed a detailed timeline of the universe, tracing it back to the first fractions of a second after the Big Bang. In that fleeting moment, a phenomenon known as inflation may have expanded space itself at an astonishing rate. Yet what triggered this inflation? Why did it begin, and what caused it to end? These questions remain unresolved. Some theories propose that the Big Bang arose from a quantum fluctuation, a ripple in the very fabric of reality that gave birth to space and time. Others suggest that the Big Bang was not the universe's first event, but merely one stage in an endless cycle of expansion, collapse, and rebirth. The mystery is deepened further by the nature of time itself. If time itself began with the universe, then asking what came before may be a question that simply cannot be answered. Our instruments, the Hubble Space Telescope, the Planck satellite, and the James Webb, offer glimpses of the universe in its earliest moments. Yet none can witness the very first instant itself. We know the universe began, we can measure its age, map its expansion, and study the aftermath. But the ultimate first cause that set the cosmos into motion, the ultimate first cause, remains shrouded in mystery. Time, as we experience it, always moves forward, yet no one fully understands why. Each moment slips from the present into the past. We remember yesterday, but cannot glimpse tomorrow. A shattered glass never reassembles itself. Heat flows from hot coffee into the air, never the reverse. This one-way flow is known as the arrow of time. What makes it puzzling is that the fundamental laws of physics do not demand it. At the tiniest scales, particles can move forward or backward in time, and the equations themselves are perfectly symmetrical. The laws of physics impose no requirement that time should move in a single direction. And yet our entire experience of reality depends on this one-way flow. Scientists often link the arrow of time to entropy, the tendency for disorder to increase. The universe began in an extraordinarily ordered state and has been drifting toward disorder ever since. But why did it start this way? Why did the cosmos emerge in such a low entropy condition that time could even have a direction? Some physicists suggest that the arrow of time may arise from the way information spreads, while others propose it is connected to the expansion of the universe itself. Yet none of these explanations fully resolve the mystery. Time's forward motion is something we live through every second, and why it moves in only one direction remains one of the most profound enigmas of science. Most of the universe is composed of something we cannot see. When astronomers study the motion of galaxies, they notice a puzzling phenomenon. Stars at the edges move far too quickly, as if held in place by an unseen force. By all logic, these stars should drift away into space, yet they remain bound. The conclusion is unavoidable. Most of the universe's mass is invisible. This mysterious substance is known as dark matter. It neither emits nor absorbs light, making it invisible to telescopes, yet its presence is undeniable because its gravity shapes galaxies, bends the paths of starlight, and leaves subtle imprints across the cosmic web. But what exactly is it? For decades, scientists have searched in vain. Some propose it consists of undiscovered particles, such as WIMPs, weakly interacting massive particles. Others suggest more exotic possibilities, ghostly particles that barely interact with ordinary matter at all. Some theories even suggest that dark matter could consist of black holes formed in the universe's earliest moments, shortly after the Big Bang. Despite decades of investigation, its true nature remains elusive. Experiments buried deep underground are poised to detect a dark matter particle colliding with a single atom, yet so far, none have succeeded. For now, this invisible mass, 5 times more abundant than ordinary matter, stands as one of the greatest mysteries in the cosmos. Meanwhile, an unseen force is causing the universe itself to expand at an ever-increasing rate. In the 1990s, astronomers observing distant supernovae expected the expansion to slow under the pull of gravity. Instead, they discovered something astonishing. The universe is not just expanding, it is accelerating. This suggests that an unknown energy embedded in space itself is driving galaxies apart at ever faster speeds. This mysterious force is known as dark energy, though the name is merely a placeholder for our ignorance. It makes up nearly 70% of the cosmos, yet its true nature remains unknown. Some scientists propose it is a property of the vacuum, a constant energy inherent in empty space. Others suggest it could signal entirely new physics, perhaps a dynamic field that evolves over time. Some theories even hint that it may reveal gaps in our understanding of gravity itself. What makes dark energy particularly unsettling is its cosmic consequence. The fate of the universe hinges on it. If it remains constant, galaxies will continue drifting apart until only emptiness remains. If it grows stronger, it could eventually tear apart galaxies, stars, and even atoms. While we can observe its effects, we cannot directly see it. Dark energy is the unseen force shaping the ultimate destiny of the cosmos. The universe seems to balance on a razor's edge. If gravity were just slightly stronger, stars would collapse too quickly. If slightly weaker, galaxies might never form. Even a tiny shift in the electromagnetic force could prevent atoms from binding together. These delicate coincidences are part of what scientists call the fine-tuning problem. Why do the laws of nature have exactly the values they do? There is no obvious reason why gravity, electromagnetism, or nuclear forces should possess their precise strengths. Yet, if they were even marginally different, life as we know it would be impossible. Some see this as mere coincidence, while others propose that countless universes exist, each with its own set of laws, and we happen to live in the rare one where conditions allow life, a cosmic lottery win of extraordinary odds. Another possibility is that an as-yet undiscovered principle dictates why the laws of nature take precisely these values. For now, we cannot know for certain. Yet, when we look at the stars, the planets, and even the very fact that we can ask these questions, it becomes clear how astonishingly suited the universe is for life, and why that remains one of science's greatest mysteries. Beyond this, the universe itself may stretch far beyond what we can observe. The observable cosmos spans roughly 90 billion light-years, yet light has only had so much time to reach us since the Big Bang, creating a horizon we cannot see past. What lies beyond it? One possibility is that the universe is infinite, extending endlessly in all directions with no boundaries. If so, space could contain an unending number of galaxies, stars, and perhaps even other Earth-like worlds. Another possibility is that the universe is finite yet unbounded, much like the surface of a sphere. In such a universe, traveling far enough in one direction could, in theory, bring you back to your starting point. Scientists search for clues in the cosmic microwave background, the faint afterglow of the Big Bang, hoping its patterns might reveal the universe's true shape. So far, evidence suggests the universe is remarkably flat, but this does not answer whether it is truly infinite. For now, we cannot know if the cosmos stretches endlessly or loops back on itself. Its full size and shape remain hidden, just beyond our reach. Beyond the horizon of what we can observe, untold mysteries may await. When we gaze into space, we are also looking back in time. The most distant galaxies visible to us emit light that has traveled for over 13 billion years, yet beyond them lies a region that will remain forever hidden. Beyond what we can observe lies the unobservable universe. This cosmic horizon is not a physical barrier, but a limit defined by the age of the universe and the speed of light. Beyond it, reality continues, but we can never know exactly what exists there. Perhaps it resembles what we see, galaxies, stars, and planets stretching far beyond our sight. Or perhaps it is profoundly different, with regions governed by unfamiliar conditions or entirely different physical laws. Some theories of inflation, the rapid expansion that occurred moments after the Big Bang, suggest that our observable universe is merely one bubble within a far larger reality. If this is true, the vast majority of the cosmos lies forever beyond measurement. We are confined to a cosmic island. The sky we see is only a tiny fraction of what may exist. The rest of the universe remains silent, unreachable, and permanently unknown.
Some scientists even propose that other universes exist beyond our own, though we cannot prove it. The idea of a multiverse is among the boldest in modern science, suggesting that our universe may not be unique, but one of countless others. Each universe within a multiverse could have its own laws of physics, unique histories, or even a different number of dimensions. This concept emerges naturally in several theories. Inflation, for example, may generate bubble universes, each forming with its own conditions. String theory predicts a vast landscape of possible realities. In such a scenario, our universe is just one outcome among countless others. This idea could even offer an explanation for fine-tuning. We inhabit a universe capable of supporting life simply because only in such universes can observers exist. Yet, there is a significant challenge. If other universes lie beyond our cosmic horizon, we may never be able to observe them. No light or signal could ever cross the boundary. This makes the multiverse both fascinating and controversial, stretching the boundaries of what we consider science, since an untestable idea may remain purely speculative. Nevertheless, the possibility that reality extends far beyond our universe, perhaps infinitely, is one of the most compelling mysteries in physics.
Space and time may emerge from deeper principles we have yet to discover. Einstein's general relativity revealed that they are not fixed backdrops, but flexible and dynamic, bending, curving, and stretching to guide the paths of planets and the flow of light. Yet at the smallest scales, relativity collides with quantum mechanics. While relativity treats space and time as smooth, quantum theory suggests they are granular, fluctuating, and uncertain. Reconciling these two views remains one of science's greatest challenges. Some theories propose that space and time are not fundamental at all, but arise from a deeper network of quantum information or entanglement patterns, giving shape to geometry itself. In this framework, what we perceive as space-time is merely a surface, underlain by a more basic reality we cannot yet observe. Others even question whether time itself is real, suggesting it might be an illusion created by deeper processes. If true, our most basic intuition about reality could be fundamentally wrong. Space and time feel like the stage on which the universe unfolds, but the stage itself may not be what it seems. What space and time truly are remains one of science's most profound, unanswered questions. At the quantum level, a single particle can exist in two places at once, and we still do not fully understand how. Quantum mechanics tells us that particles do not possess definite positions until they are measured. Instead, they exist in a superposition, a probabilistic cloud where multiple outcomes coexist simultaneously. An electron, for example, can pass through both slits in an experiment at the same time, interfering with itself like a wave. Only when we observe it does the particle assume a definite position. This is not merely theoretical. Experiments have demonstrated superposition in action, not just with electrons, but with molecules thousands of times larger. Physicists can even engineer delicate states in which objects exist in overlapping possibilities. And yet, despite all this, the true meaning of these phenomena remains one of the greatest mysteries in science. Does a particle truly exist in two places at once, or is superposition merely a reflection of our limited knowledge? Some interpretations propose that multiple realities split, one where the particle lands here, another where it lands there. Others suggest that reality itself remains indeterminate until it is measured. Whatever the explanation, the ability of a single particle to seemingly occupy two locations simultaneously is one of the strangest and most unsettling mysteries of modern science. Even more puzzling, entangled particles can echo each other across light years, defying conventional understanding. When two particles become entangled, their properties are linked in a way that transcends distance. Measuring one instantly reveals the state of the other, no matter how far apart they are.
Einstein famously referred to this as spooky action at a distance because it appeared to violate the cosmic speed limit. Nothing should move faster than light. Yet experiments consistently confirm that entanglement is real. Photons, electrons, and even small clusters of atoms have been entangled and separated by kilometers. No signal appears to travel between them, and yet their correlations remain perfectly synchronized. It is as if nature maintains a hidden ledger, ensuring outcomes stay in harmony. What does this imply? Some physicists propose that reality is fundamentally non-local, woven together more deeply than space and time would allow. Others suggest entanglement hints at hidden variables we have yet to uncover. Still others argue that information itself may form the very foundation of reality. While we harness entanglement in quantum computing and secure communication, we still cannot fully explain why it works. The universe seems to whisper across vast distances, and we are left wondering how. Similarly, no one truly knows why simply observing something can appear to alter what it is. One of the most perplexing discoveries in physics is that the very act of measurement can influence the system being observed. In the famous double-slit experiment, particles behave like waves when unobserved, forming interference patterns on a screen. Yet the moment we measure which slit a particle passes through, this wave-like behavior disappears. The outcome changes simply because it was observed. Why does this happen? One explanation is that the wave function, which mathematically describes all possible states, collapses into a single outcome upon observation. But what qualifies as an observer? Is it a measuring device, a human consciousness, or something else entirely? Some interpretations suggest that every possibility occurs, branching into multiple universes. Others propose that particles only become definite when information about them becomes irreversible. To this day, none of these ideas have been definitively proven. What we do know is that the boundary between observer and observed is far more complex than we once imagined. The universe appears to respond to being watched, and no one truly understands why. Meanwhile, gravity remains one of the great puzzles of physics. It governs the cosmos, keeping planets in orbit, shaping galaxies, and controlling the motion of stars. And yet, compared to the other fundamental forces, it is astonishingly weak. A small refrigerator magnet can easily overpower the gravitational pull of the entire Earth. Why is this so? The electromagnetic force, the strong nuclear force, and the weak nuclear force all operate over tiny scales with immense strength, while gravity seems feeble by comparison. Physicists have wrestled with this hierarchy problem for decades. One possibility is that gravity extends into hidden dimensions we cannot perceive, diluting its apparent strength. Another is that gravity is intrinsically strong, but its true effects are masked by unknown physics at microscopic scales.
Despite centuries of study, the question of why gravity is so much weaker than the other fundamental forces remains unanswered. This imbalance is not merely a curiosity, it is essential to the structure of the universe. Without it, stars and galaxies could not form. In this quiet weakness lies the hidden mechanism that makes the cosmos possible. Meanwhile, Einstein's theory of general relativity and the laws of quantum mechanics both work remarkably well, yet they stubbornly refuse to align. General relativity describes the large-scale universe with extraordinary precision, while quantum mechanics explains the microscopic world with astonishing accuracy. Each has been rigorously tested and confirmed, yet they clash when applied together. In extreme conditions, inside black holes or during the first moments of the universe, the equations break down, with infinities piling upon infinities. The two frameworks are mathematically incompatible. Physicists have searched for decades for a unifying theory of everything that could reconcile these two pillars of modern science. Candidates such as string theory and loop quantum gravity offer tantalizing possibilities, yet no experiment has confirmed them. Without a unifying theory, we cannot fully understand the birth of the cosmos or the nature of space-time at its smallest scales.
The fact that our two most successful theories describe different aspects of reality is among the greatest paradoxes in science. Both work perfectly on their own, yet together they fail. Nowhere is this conflict more apparent than in black holes. These are regions where gravity is so intense that nothing, not even light, can escape. As matter falls inward, it is compressed toward the center. According to Einstein's equations, it collapses into a single point of infinite density known as a singularity. But infinities often signal a breakdown in our mathematics. What truly lies at the heart of a black hole? Some physicists argue the singularity is real, a place where the laws of physics collapse. Others believe a deeper theory, such as quantum gravity, could replace it with something else, a looped structure of space-time, a finite core, or an entirely new kind of object beyond our current comprehension. The event horizon shields the interior completely from view. For now, the heart of a black hole remains inaccessible, sealed beyond observation and certainty, one of the most profound mysteries in all of science. We still do not truly understand what singularities are. A singularity is a point where our equations predict infinities, density without limit, curvature without bound, and time and space collapsing into something beyond definition. Black holes contain them, and the Big Bang itself may have begun with one. But what are they in reality? Are singularities genuine features of nature, or simply indicators that our current theories are incomplete? Many physicists believe they reveal the limits of Einstein's relativity. Beyond this boundary, a new framework, a theory that unites relativity with quantum mechanics, must take over to explain what truly exists at these extremes. In a complete theory, these infinities might resolve into something finite and understandable. Until such a framework exists, singularities remain some of the deepest puzzles at the edge of physics, regions where our understanding stops and our equations break down. What lies beyond them is hidden, awaiting a deeper theory of reality. One of the most intriguing questions concerns information in black holes. When matter falls in, it appears to vanish forever. Yet in physics, information, the details of a system's state, should always be preserved. So what happens to the information trapped inside a black hole? Stephen Hawking showed that black holes can gradually evaporate through radiation, but if they disappear entirely, where does the information go? If it is destroyed, it would violate the principles of quantum mechanics. If it escapes, it must somehow be encoded in the Hawking radiation, a process that remains poorly understood. This conundrum, known as the black hole information paradox, has challenged physicists for decades and continues to drive the search for a deeper understanding of the universe. Some physicists propose that the information may be stored on the event horizon itself. Others suggest that black holes could connect to distant regions of spacetime, allowing information to escape. Still, some argue that our understanding of quantum mechanics itself may need revision. The fate of information in a black hole remains one of the most profound open questions in physics, touching not only on black holes, but on the very foundations of reality. While Hawking radiation is a cornerstone prediction, it has never been directly observed. In the 1970s, Stephen Hawking made the astonishing prediction that black holes are not truly black. Quantum effects near the event horizon should cause them to emit faint radiation, gradually losing mass over incomprehensibly long timescales. In theory, they could eventually evaporate completely. This emission, now known as Hawking radiation, remains one of the most iconic predictions in modern physics. Yet, we have never directly observed it. Real black holes are shrouded in hot gas and violent surroundings that easily mask the faint trickle of radiation. With current technology, detecting it may be impossible. Still, the concept carries profound implications. It links quantum theory, relativity, and thermodynamics, suggesting that black holes possess a temperature and that space-time itself is far more dynamic than we had imagined. Laboratory experiments have attempted to simulate Hawking radiation using sound waves and fluids, but these remain indirect analogs rather than direct evidence. Whether Hawking radiation truly exists is still unproven. If it does, it would fundamentally reshape our understanding of black holes. If it does not, then something even stranger must be occurring at the edges of space-time. Black holes may even serve as gateways to other worlds we have yet to discover. In every sense, they push physics to its limits, bending space and time in ways we cannot fully describe.
Some solutions to Einstein's equations suggest that black holes could connect to other regions of spacetime through tunnels known as wormholes. In theory, passing through a black hole might lead somewhere else, but this remains speculative. If wormholes do exist, they may be highly unstable, with the extreme gravity of a black hole destroying anything that tries to traverse them. Yet the mathematics leaves the possibility open. Some physicists propose that the singularity at a black hole's core could serve as a bridge to an entirely new universe with its own dimensions of space and time. Others suggest that black holes might recycle information, seeding the formation of new cosmic regions. For now, these ideas cannot be tested, as no signal can escape a black hole's interior. Its secrets remain concealed, yet the notion that black holes could be more than cosmic graves, that they might act as gateways to something beyond, remains one of the most tantalizing mysteries in science. Beyond these enigmas, we are still searching for answers to another profound question: how the very first stars in the universe were born. When the universe was young, it was a dark and simple place. There were no galaxies, no planets, no metals, and no complex chemistry, only vast clouds of hydrogen and helium drifting through the expanding cosmos. At some point, these primordial clouds collapsed under gravity to form the very first stars, ending the cosmic dark ages and illuminating the universe for the first time. Yet the precise process behind their formation remains a mystery. These earliest stars, known as population 3 stars, would have been enormous, hundreds of times the mass of our Sun, burning intensely and briefly, lasting only a few million years before exploding as powerful supernovae. In doing so, they forged the universe's first heavy elements, laying the foundation for later generations of stars, and ultimately the possibility of life. The challenge is that none of these first-generation stars has ever been directly observed, leaving their existence and properties inferred but unconfirmed. These first stars lived and died so rapidly, so long ago, that direct evidence of them is lacking. Astronomers search for indirect clues, such as the chemical fingerprints left in ancient stars, hoping to uncover traces of these violent early events. The James Webb Space Telescope may one day capture the faint light of these primordial stars. For now, however, the exact mechanisms that ignited the first stars remain one of astronomy's greatest open questions. Meanwhile, some galaxies formed supermassive black holes far too quickly. At the center of nearly every galaxy resides a supermassive black hole, millions or even billions of times the mass of our Sun. While we understand how black holes can grow by accreting gas, stars, and merging with other black holes, observations of the early universe revealed giants that grew astonishingly fast. Some of these colossal black holes already existed less than 1 billion years after the Big Bang, challenging our understanding of cosmic evolution. According to current models, there simply wasn't enough time for these black holes to grow so massive through conventional processes. This presents a profound puzzle. Did they form directly from the collapse of enormous primordial clouds, bypassing smaller stages of growth? Were they born from the deaths of the earliest massive stars, collapsing into black holes far larger than expected? Or is there an entirely unknown mechanism that allowed them to feed and expand at extraordinary rates? These ancient supermassive black holes challenge our understanding of galaxy formation. Solving their mystery could reveal how galaxies themselves came into existence. For now,
they remain cosmic enigmas, colossal structures that seemingly should not exist so soon after the universe began. Beyond this, the question of why so many galaxies adopt spiral shapes continues to intrigue astronomers. When we picture galaxies, we often imagine graceful spirals, their stars sweeping outward in elegant cosmic pinwheels. Our own Milky Way is a prime example. Yet why galaxies adopt such intricate spiral patterns remains a mystery. One explanation is that spiral arms are density waves, similar to traffic jams on a highway. Stars move through these regions, clustering as they pass, giving the appearance of persistent arms. Another theory proposes that spiral structures arise from gravitational interactions as galaxies tug on one another, stirring stars into curving formations. While simulations can reproduce spiral patterns, they do so imperfectly, and the exact mechanisms remain uncertain. Spiral galaxies are common, yet the reason why some galaxies develop these stunning forms while others become featureless elliptical shapes is still one of astrophysics' enduring questions. When we gaze at the night sky and see the Milky Way arcing above us, we are looking from within one of the universe's greatest mysteries. The sweeping arms of our home galaxy are both familiar and inexplicably complex. Across the cosmos, fast radio bursts continue to baffle astronomers. The first of these signals was detected in 2007, lasting only a few milliseconds, yet releasing as much energy as the sun emits in an entire year. Since then, hundreds more have been observed, scattered across the sky. Some of these bursts repeat, hinting at ongoing processes such as magnetars, neutron stars with extreme magnetic fields capable of unleashing tremendous energy. Others appear only once, suggesting catastrophic events like the collapse of a massive star or the merger of compact objects. No single explanation accounts for all fast radio bursts. As these signals traverse billions of light years, they are distorted and stretched by the matter between galaxies, offering astronomers a potential tool to map the distribution of matter throughout the universe. Until we uncover their origins, fast radio bursts remain enigmatic cosmic puzzles. Every so often, the universe sends out a brief, powerful signal across the void. We can detect it, measure it, yet we still do not know what or who is producing it. Pulsars, on the other hand, emit radiation with astonishing regularity, a precision that continues to baffle scientists. These objects are the collapsed remnants of massive stars, neutron stars spinning rapidly, sweeping beams of radiation across space like cosmic lighthouses. Discovered in 1967, their initial regularity led some to wonder if they were messages from intelligent life. Today, we understand them to be natural phenomena, yet their consistency remains remarkable. Some pulsars keep time even better than our most accurate atomic clocks, rotating hundreds of times per second without deviation. How such a dense city-sized star maintains this stability is still not fully understood, though it relates to their immense density and powerful magnetic fields. Pulsars can also experience sudden glitches, abrupt changes in rotation speed, likely caused by complex interactions within their superfluid cores, an environment unlike anything found on Earth.
Pulsars serve as natural laboratories of extreme physics, yet they continue to conceal many secrets. Their precise rhythms remain among the most mysterious signals in the universe. Even more enigmatic are magnetars, neutron stars with magnetic fields 1,000 times stronger than typical neutron stars and 1,000,000,000,000 times stronger than Earth's. These immense magnetic forces twist, snap, and release sudden, violent bursts of radiation.
In a single second, a magnetar can emit more energy than the sun produces in 100,000 years, detectable as intense X-ray and gamma-ray flares. What triggers these eruptions is still uncertain. Are they caused by starquakes, shifts in the neutron star's crust under magnetic stress, or sudden reconfigurations of the magnetic field, releasing energy like a snapping cosmic rubber band? Some fast radio bursts have even been linked to magnetars, hinting that they may explain at least part of these mysterious signals. Though only a few dozen magnetars are known, their immense power reminds us that the universe harbors energy engines far beyond our current understanding. Adding to the mystery, cosmic rays, high-energy particles, strike Earth continuously, yet their origins remain unknown. Most cosmic rays are protons traveling close to the speed of light, often originating from the sun or supernova explosions. Yet some are so extraordinarily energetic that their sources remain a mystery. The most extreme cosmic rays carry the energy of a fast-pitched baseball concentrated into a single particle, a feat no known process should be able to achieve. They may be born near supermassive black holes, within active galaxies, or through exotic, unknown mechanisms. When these particles strike the Earth's atmosphere, they create showers of secondary particles that can be detected on the ground. Observatories such as the Pierre Auger Observatory in Argentina attempt to trace their paths back to their sources, but interstellar magnetic fields bend their trajectories, erasing critical clues. Cosmic rays constantly bombard our planet, yet the origins of the most powerful among them remain unexplained, hinting at natural particle accelerators far beyond human capabilities. Across the vastness of space, immense cosmic voids stretch between galaxies, their origins equally puzzling. Rather than being evenly distributed, matter forms a colossal cosmic web, clusters and filaments of galaxies separated by enormous voids, some spanning hundreds of millions of light years, nearly empty of any visible matter. Why do these immense voids exist? Simulations suggest that gravity naturally draws matter into filaments, leaving vast, empty regions behind. Yet the largest voids are far bigger than expected, raising intriguing questions about their formation. Could they hint at new physics, perhaps in how dark energy influences cosmic structure? Or are they simply statistical outliers, rare but possible? These voids also affect the way light travels across the universe and may hold subtle clues about the nature of dark energy itself. For now, their true origins remain a profound mystery. Gazing into a cosmic void is like peering into the largest emptiness imaginable, some of the loneliest expanses in existence, vast and unexplained. The ultimate fate of the universe remains equally uncertain. While we know the universe had a beginning, will it also have an end? Scientists explore several possibilities, each depending on the nature of dark energy and the interplay of cosmic forces. In one scenario, the universe continues to expand indefinitely, gradually cooling as stars burn out and galaxies fade into darkness, a fate known as heat death. Alternatively, the expansion could eventually reverse, collapsing everything back into a dense state in a big crunch. A third possibility, the Big Rip, envisions dark energy growing stronger over time, tearing galaxies, stars, planets, and even atoms apart. Each outcome paints a profoundly different vision of the universe's final chapter, yet which path awaits remains unknown. Which fate will the universe ultimately follow? We simply don't know. Observations indicate that expansion is ongoing, yet the precise nature of dark energy remains too uncertain to draw definitive conclusions. The cosmos could endure for trillions of years, or it could meet a far more dramatic end. For now, the ultimate destiny of stars, galaxies, and even life itself remains one of science's most profound unanswered questions. Something triggered a period of cosmic inflation, but its origin remains a mystery. In the first fraction of a second after the Big Bang, the universe is believed to have expanded faster than the speed of light in a process known as inflation. This theory helps explain why the cosmos appears remarkably smooth and uniform, and why tiny fluctuations in the early universe later grew into the galaxies we observe today. But what set inflation in motion? The answer is unknown. Some theories suggest a field of energy called the inflaton briefly dominated the cosmos before fading. Others link inflation to the quantum fabric of space-time itself. Evidence of this rapid expansion can be seen in the cosmic microwave background, where subtle patterns align with inflationary predictions. Yet the true cause and even the precise details of inflation remain subjects of active debate. Whatever the mechanism, something caused the universe to grow unimaginably fast, laying the foundation for everything that followed. Yet the initial spark that set inflation in motion remains unknown, a hidden chapter in the story of creation. Similarly, the origin of life on Earth continues to elude us. Life began over 3.5 billion years ago, but the precise circumstances remain shrouded in mystery. Fossil evidence shows that microorganisms were already flourishing not long after the planet cooled. But how did non-living chemistry transform into living systems? One possibility is that simple molecules self-organized into chains capable of storing information, perhaps RNA before DNA. Another suggests life emerged in the energy-rich environment of hydrothermal vents, where hot water, minerals, and complex chemistry combined. Some researchers even propose that life's building blocks arrived from space, delivered by comets or meteorites bombarding the young Earth. Each idea has supporting evidence, yet none can be definitively proven. Laboratory experiments have successfully created amino acids and other fundamental molecules under conditions thought to resemble early Earth, but producing a fully living system remains beyond reach. The origin of life may have been a unique event, or perhaps it is a natural outcome whenever conditions align. Until more concrete evidence emerges, the moment when chemistry first awakened into biology remains one of science's deepest mysteries. Even the question of where life began, ocean or land, remains unresolved. Our planet offered multiple potential cradles for the first life, each with its own tantalizing possibilities.
The vast oceans covering much of early Earth seem like a natural cradle for life. Hydrothermal vents, where mineral-rich hot water gushes from the seafloor, provide a constant source of energy and complex chemistry. Many scientists suggest that life could have begun here, with molecules assembling inside natural mineral compartments. Yet another possibility exists. Some researchers propose that shallow pools on land, repeatedly drying and refilling, may have concentrated molecules, driving the chemical reactions needed to form life's building blocks. Ultraviolet sunlight, often destructive, could also have supplied the energy for key steps in these reactions. Both scenarios are compelling. Oceans offer stable energy, but dilute molecules, making interactions less likely. Land-based pools could concentrate molecules, but were potentially unstable. Until stronger evidence is found, we cannot say whether life first awakened in the deep ocean or in sunlit shallow waters on land. The answers lie buried deep in Earth's ancient past, locked in rocks and fossils long transformed. How the very first living cells emerged remains unknown. Life is not merely chemistry, it is organization. Modern cells are complex structures, complete with membranes that separate them from their environment and molecular machinery carrying out countless reactions. But how did the first cell come into being?
One compelling idea suggests that fatty molecules on early Earth naturally formed tiny bubbles, creating primitive membranes. These nascent compartments could have trapped and protected fragile chains of RNA or proteins, while still allowing energy and essential molecules to flow in and out. Over time, the chemistry within these early enclosures may have grown increasingly complex, eventually giving rise to self-sustaining systems, the earliest forms of life on our planet. Was the emergence of life a predetermined outcome of chemistry, or a rare cosmic accident, a single success among countless failures? The universality of DNA hints that life may have discovered an optimal solution, yet why evolution chose this precise path remains one of the deepest mysteries of existence. Viruses add yet another layer of intrigue. Straddling the boundary between life and non-life, they cannot reproduce on their own, relying entirely on the machinery of living cells. And yet, they evolve, adapt, and exert profound influence over the course of life on Earth. Their origins remain uncertain. Some scientists suggest that viruses are remnants of the ancient RNA world, predating fully formed cells. Others propose they began as fragments of genetic material that escaped cells and learned to replicate independently. A third theory envisions viruses as once fully living organisms, later reduced to their simplest form. Each possibility reminds us how much remains unknown about the earliest and most enigmatic players in the story of life. The truth may be that viruses emerged through multiple pathways, their origins as varied and complex as life itself. What is certain is that they are ancient, and they may have played a pivotal role in the evolution of complex organisms, transferring genes across species. Viruses blur the boundary between life and non-life, and their beginnings remain one of biology's most enduring mysteries. Meanwhile, the earliest molecules on Earth followed paths both ordinary and extraordinary. The young planet was a vast chemical laboratory, with simple compounds forming everywhere, from hydrothermal vents on the ocean floor to volcanic pools and lightning-scorched atmospheres. Among this abundance, some molecules began linking into more complex chains, such as amino acids and nucleotides. Yet only a tiny fraction of these chemical interactions ultimately crossed the threshold into life as we know it, setting the stage for biology as we know it. Why did certain molecules succeed while countless others failed? What special qualities allowed some to organize into self-replicating systems? Was life an inevitable result once the right ingredients came together, or a rare accident shaped by chance? Experiments show that many of life's building blocks can form naturally, yet producing a fully self-sustaining, evolving system remains beyond our reach. The jump from chemistry to biology is enormous, and exactly how it occurred is still a mystery. This uncertainty raises profound questions. If life is a natural outcome, the universe could be filled with living worlds. If it was a rare fluke, we might be astonishingly alone. Understanding why some molecules became alive while others stayed inert remains one of science's deepest unresolved puzzles.
We also do not yet know whether life exists elsewhere. Earth is the only known home of life, but with billions of stars in our galaxy and countless galaxies beyond, it seems improbable that we are entirely alone. Despite decades of exploration, definitive evidence of extraterrestrial life remains elusive. Thousands of exoplanets have been discovered, many lying within habitable zones where liquid water could exist. Organic molecules are abundant in space, found on comets, in interstellar clouds, and on distant moons. Even Mars shows traces of a wetter past, suggesting that the ingredients for life may have been present elsewhere in our solar system. Beneath the icy shells of moons like Europa and Enceladus lie vast hidden oceans, hinting that conditions suitable for life may be far more common than we once imagined.
Yet, despite these promising environments, the universe remains silent. We have not detected alien signals, found microbial life on Mars, or uncovered fossilized evidence of life beyond Earth. Perhaps life is widespread but difficult to detect, or perhaps it is exceedingly rare, requiring conditions we have yet to understand. Until we discover even the simplest extraterrestrial organism, the question of whether life exists elsewhere remains unanswered. Could life arise from a chemistry entirely different from what we know? All known life on Earth relies on carbon, water, DNA, and proteins, but must it be this way? Some scientists propose silicon, abundant and capable of forming long chains as an alternative foundation. Others envision organisms using ammonia instead of water, or thriving in methane seas such as those on Saturn's moon Titan. Even more speculative ideas suggest that life could even emerge from plasma, magnetic fields, or pure information. For now, these possibilities remain open, highlighting the profound mystery of life's potential diversity in the cosmos. All of our current definitions of life are based on a single example: Earth. It may be that carbon and water are the only viable foundations for life, or the universe may harbor forms of life far stranger than we can imagine. If we ever discover extraterrestrial life, it could challenge our very understanding of what it means to be alive, appearing in ways completely unlike anything on Earth. The question of how common truly habitable worlds are remains unresolved. Astronomers have identified thousands of exoplanets orbiting distant stars. Some are rocky and lie within the so-called habitable zone, where liquid water could exist. Yet habitability depends on far more than distance from a star. Planets require the right atmospheric conditions, magnetic shielding, and long-term orbital stability. Some may be scorched by radiation, others frozen in perpetual cold. Moons with subsurface oceans may also be hospitable, but current technology cannot yet measure them directly. The galaxy could be teeming with worlds capable of supporting life, or they could be rare, exceptional jewels. Each new discovery brings us closer to understanding, but the true abundance of Earth-like environments remains one of astronomy's most compelling mysteries. The oldest question of all still eludes us. Are we alone? For as long as humanity has gazed at the stars, we have wondered whether life exists beyond Earth. Despite the vastness of the cosmos, the abundance of planets, and the widespread availability of life's building blocks, we have no definitive answer. We scan the skies with radio telescopes, send probes to distant worlds, and study the atmospheres of exoplanets for signs of life. Yet the universe remains silent. Life may be common, but intelligent civilizations could be rare or ephemeral. Perhaps life itself is scarce, making Earth an extraordinary exception. Or it could be widespread, but separated from us by immense distances or fundamentally different forms that we cannot recognize. The question endures: are we a solitary spark in a vast emptiness, or one voice among countless others in a cosmic chorus yet to be heard? Until evidence emerges, this most ancient and profound question remains unanswered. Consciousness emerges from the brain, yet its true nature remains a profound mystery. Every thought, every memory, every fleeting moment of awareness seems to arise from neural activity. Scientists can measure electrical signals racing across neurons, alter consciousness with anesthesia, and even observe how the brain responds when you focus on an image or sound. But none of this reveals why subjective experience exists at all. Why does the firing of neurons produce the sensation of being alive? A brain scan may light up the visual cortex when you see a sunset, yet it cannot capture the vivid glow of red and gold you experience internally. It can map circuits for hearing, but it does not explain why listening to a favorite song stirs emotion. Some researchers suggest consciousness arises when information spreads across the brain, when neurons form particular patterns, or even as a fundamental property of the universe itself. Yet none of these explanations fully bridge the gap from matter to mind. Consciousness is perhaps the most familiar yet mysterious aspect of existence. It is what you are experiencing in this very moment, and yet when we try to explain it, it evades understanding. While we know it emerges from the brain, the mechanism behind it remains one of science's deepest enigmas. Dreams are another puzzle. Every night, the mind conjures entire worlds, some vivid, populated with familiar faces and places, others strange, fragmented, and fleeting, disappearing upon waking. Despite their universality, the purpose of dreams is still uncertain. Some researchers suggest dreams allow the brain to rehearse and strengthen important memories. Others propose they help regulate emotions, offering a safe space to process fear, sadness, or conflict. Another idea is that dreams are simply the result of random neural activity woven together into narratives by the sleeping brain. What makes dreams especially compelling is their intensity. A nightmare can jolt you awake in fear, even while you lie perfectly safe in bed.
A joyful dream can leave a lingering sense of happiness long after waking. Occasionally, dreams even spark solutions to problems. Writers, artists, and scientists alike have reported insights and breakthroughs that came to them in sleep. During dreaming, the brain is remarkably active, particularly during rapid eye movement sleep, when the eyes flicker beneath closed lids. Yet the deeper purpose of dreaming remains a mystery. Dreams take us on nightly journeys through strange and unfamiliar landscapes, yet their true meaning continues to elude us. Similarly, our perception of time is deeply subjective. Moments of fear or intense focus can feel like they stretch endlessly, while hours spent absorbed in joy may vanish in an instant. While the clock ticks uniformly, our inner sense of time is fluid and unpredictable. Some researchers propose that an internal brain clock governs this perception, accelerating during high emotion states and slowing during calm periods. Others suggest that our brain measures time by the number of events it processes. A day packed with novel experiences feels long, while routine moments seem fleeting. This may explain why childhood summers felt endless, while the years of adulthood seemed to slip by in a blur. Novel experiences stretch our perception of time, while routine compresses it. But this remains a theory. What we do know is that mental time is elastic. Seconds and minutes tick steadily on the clock, yet our experience of them flows according to patterns we do not fully understand. Memory adds another layer of mystery. Every moment of your life, your first day at school, your happiest achievements, your deepest regrets, is stored somewhere in the brain. But how these memories are maintained and later recalled remains largely unknown. Memories are not like neatly filed documents. They are patterns of activity distributed across networks of neurons in different brain regions. The hippocampus acts as an index, helping organize and retrieve these patterns, yet the precise mechanisms of encoding and recall remain elusive. Memories are dynamic. Each time we recall them, they can be reshaped, and in some cases, false memories can form, feeling as vivid and real as authentic experiences. Why do some memories last a lifetime, while others fade within days? Why can a single smell suddenly unlock a vivid scene from childhood? Experiments reveal glimpses, neurons that fire when a particular face is seen, brain activity that mirrors memory recall, yet the full picture remains hidden. Memory is the glue that shapes our identity, and how moments become part of us or resurface years later remains one of the brain's deepest mysteries. Emotions are equally enigmatic. They shape every aspect of life. Joy propels us forward, fear holds us back, anger flares, sadness weighs heavy. But where do these feelings originate?
Scientists know that emotions involve both the brain and the body. Your heart races in fear, your stomach knots in anxiety, tears form in sadness. Yet their origins are still debated. Are emotions hardwired survival tools, inherited from our evolutionary past? Or are they constructed by the brain, influenced by memory, culture, and interpretation? Certain brain regions play roles: the amygdala in fear, the insula in disgust, the prefrontal cortex in regulation, but no single center governs any emotion. Music can give us goosebumps, scents can awaken waves of nostalgia. The way our minds translate experience into feeling remains one of science's greatest mysteries. Sometimes we don't even know why we feel the way we do. Emotions are powerful guides, steering our choices often more than reason. Yet how they arise, how they take hold of both body and mind, remains one of the most intimate mysteries of being human. Creativity is just as elusive. An artist stares at a blank canvas, a writer at an empty page, a scientist at an unsolved problem. Hours may pass in silence, and then suddenly an idea appears, vivid, surprising, alive. Where does it come from? Creativity feels like a spark, yet its origin remains hidden. Some suggest it is the brain mixing and recombining old ideas in novel ways. Others propose it emerges when the subconscious works quietly while the conscious mind rests. Many historical breakthroughs occurred not at desks, but in dreams, showers, and long, quiet walks. Brain scans reveal networks generating ideas and others judging them, yet still the moment of inspiration itself remains a profound mystery. Why does a solution sometimes arrive suddenly with such force? Why do some people overflow with creative ideas while others struggle? Creativity is one of humanity's greatest gifts, shaping art, science, and progress. Yet the place where ideas come from, the quiet leap from nothing to something, remains a mystery we cannot explain. Déjà vu makes the present feel eerily repeated, and no one knows why. You step into a room you've never seen before, yet everything feels strangely familiar. You sense what might happen next, though you have no real memory of it. Scientists suggest it may be a trick of memory. The brain misfires, creating a false signal of familiarity. Others propose that one part of the brain processes an experience slightly before another, making the moment feel like a repeat. Others think it arises from subtle similarities between a current scene and a forgotten past one, fooling the mind. What makes déjà vu so mysterious is its intensity. For a few seconds, reality feels doubled, both new and remembered. Almost everyone experiences it, yet no one can predict when or why. Déjà vu reminds us that memory and perception are fragile, that the brain sometimes tricks us in ways we do not yet understand. Placebos can heal, but the power behind them is equally puzzling. Imagine taking a pill, being told it will ease your pain, and actually feeling better, even though the pill contains nothing at all. This is the placebo effect, and it is real. Doctors have seen placebos reduce pain, ease depression, and even calm symptoms of Parkinson's disease. The effect seems to come from expectation. The belief that something will help triggers real changes in the brain and body. Placebos can release natural painkillers, alter brain chemistry, and influence the immune system, showing that the mind can profoundly shape the body, even in ways we don't yet fully understand.
What makes the placebo so strange is that it can work even when people know they are taking one. Somehow, the ritual of treatment, the pill, the doctor, the expectation, taps into hidden pathways in the mind and body, easing pain, calming symptoms, and even promoting healing. Yet why some respond strongly while others do not remains unknown. The placebo effect blurs the boundary between mind and body, revealing that belief itself can alter reality in ways science still cannot fully explain. And then there is sleep. Every night we surrender to it, closing our eyes, drifting into dreams, losing awareness for hours.
Yet why we need it remains one of nature's deepest mysteries. Sleep is dangerous. An animal in the wild is vulnerable while it slumbers, yet every species does it, suggesting it is essential. Essential for what? Perhaps to store memories and learn. Perhaps to clear away waste, scrubbing the brain of harmful buildup. Perhaps to restore energy, regulate emotions, strengthen the immune system, or even to rewire the brain, balancing connections. Sleep may do all these things, or something we have yet to discover. No single explanation fits, and the mystery remains. Different animals sleep in very different ways. Dolphins rest with only half their brain at a time. Some birds even sleep while flying. Some creatures need remarkably little sleep at all. What we do know is that without sleep, minds and bodies rapidly break down. Yet we spend roughly a third of our lives doing it, and the reason remains one of science's great mysteries. Aging is another puzzle. Every living being on Earth grows old. Skin wrinkles, hair grays, muscles weaken, and eventually the body begins to fail. Yet science cannot fully explain why aging happens or why it occurs so differently across species. One explanation points to DNA. Each time a cell divides, the protective caps on chromosomes, called telomeres, grow shorter. Eventually, the cell stops dividing. Another theory blames damage. Oxygen molecules and other byproducts slowly corrode cells, leaving scars that accumulate. Some see aging as an evolutionary trade-off, prioritizing energy for reproduction in youth while leaving the body vulnerable later. But nature offers surprises. Some turtles and fish show almost no signs of aging. Certain jellyfish can revert to earlier life stages, sidestepping decline altogether. Naked mole rats live far longer than expected, resisting age-related decline. Some clams have been discovered alive after more than 500 years. Why do some creatures resist aging while humans succumb to it? And why does the process unfold with such predictability in us? The answers remain elusive. Unlocking this mystery could revolutionize medicine, but for now, aging is a riddle written into our very cells. The limits of human lifespan are uncertain. The longest confirmed life ended at 122 years. Is this the upper boundary of human biology or merely a rare anomaly? No one knows. Some researchers argue humans have a hard limit. Beyond a certain age, the body can no longer repair itself quickly enough to survive. Evidence shows survival rates drop sharply after 110, hinting at a biological ceiling. Others suggest there is no strict maximum, only ever-increasing odds of frailty, disease, and chance. What's striking is that while average life expectancy has soared thanks to medicine, hygiene, and nutrition, the maximum lifespan has barely shifted. Almost no one lives past 115, regardless of era or location. Yet scientists continue to search for ways to push this boundary, hoping to unravel the secrets hidden in ourselves and perhaps extend life beyond what we now consider possible. Scientists study families of superagers who remain healthy into extreme old age, searching for genes that resist disease and testing drugs that slow aging in animals.
Could humans someday live to 150 or even 200? The data offers hints, but no certainty. The upper boundary of human life remains hidden, waiting for someone to discover whether it is fixed or can be pushed further. Regeneration adds another layer of mystery. Some animals can regrow entire limbs, and we cannot explain how. Salamanders replace lost legs. Starfish rebuild missing arms. Certain worms can regenerate an entire body from a single fragment. In humans, regeneration is minimal. A child may regrow a fingertip, but a lost limb never returns. Why them and not us?
Studies show that when salamanders are injured, cells near the wound reset, reverting to a flexible, embryonic-like state. From there, they rebuild muscles, bones, and nerves perfectly. Humans share many of the same genes, yet our bodies do not use them in the same way. Unlocking this ability could transform medicine. Damaged hearts could repair themselves, spinal cords could regrow, lost limbs could return. And yet, despite decades of research, the full blueprint of regeneration remains hidden, another profound mystery written into the fabric of life. Why nature granted some creatures extraordinary longevity while denying it to others remains a mystery. For now, the secrets of regeneration and extended life belong to salamanders, starfish, and a few exceptional species, a miracle we can only observe with awe. Most animals follow simple rules. Small bodies live short lives, large ones live longer. Mice live a few years, elephants many decades. Humans, with our long lifespans, are outliers among primates. Yet scattered across nature are creatures that defy these rules entirely. The Greenland shark drifts beneath Arctic ice for centuries, living more than 400 years. Bowhead whales glide through frozen seas for over 2 centuries. Tiny naked mole rats live 10 times longer than similar rodents, resisting age-related decline. Some clams have been discovered alive after more than 500 years.
Why do these creatures live so long? Scientists have uncovered clues, unusual proteins that resist damage, DNA repair systems that operate with remarkable efficiency, and metabolisms that move at glacial speeds. Yet no single answer explains them all. Each species seems to hold its own key to longevity, a puzzle humans cannot yet replicate. These extraordinary lives remind us that aging is not a fixed law of nature, but a riddle with many solutions waiting for discovery. If we could learn their secrets, we might one day unlock new ways to extend our own lives. For now, they remain timeless enigmas of the natural world. Some animals survive being frozen solid, yet their mysteries remain hidden. Imagine being frozen into ice, blood crystallized, heart silent, body rigid. For most creatures, this means death, but not for all. The wood frog of North America freezes solid in winter. Its heart stops, its body stiffens, yet when spring arrives, the frog thaws and hops away unharmed. Certain insects and fish can do the same, and tardigrades, tiny water bears, endure extremes far beyond freezing, even surviving the vacuum of space. How do they do it? Some fill their bodies with special antifreeze molecules that prevent ice crystals from shredding cells. Others use sugars to stabilize tissues during freezing. Yet the exact details of how their brains, hearts, and delicate organs survive months without activity remain unclear. If we could master this trick, it could revolutionize organ transplants, medicine, and even space travel. We might preserve organs for months or place humans into hibernation for long journeys. But for now, the secret belongs only to these hardy survivors, creatures that seem to laugh at the laws of life and death. Some whales live for centuries without succumbing to cancer, and no one knows how. The bowhead whale can live for over 200 years, gliding through icy Arctic waters, a living testament to nature's enduring mysteries. What makes this astonishing is not just the age of these creatures, but their health. Despite their massive size, with billions of cells and centuries for mutations to accumulate, cancer is remarkably rare. This is known as Peto's paradox,
Larger animals, in theory, should face higher cancer rates, yet whales, elephants, and other giants defy expectation. In elephants, researchers have discovered extra copies of tumor suppressor genes, providing additional layers of defense. In whales, the answer is murkier. Perhaps their DNA repair systems are unusually robust. Perhaps their metabolism slows damage. Perhaps they harbor unique biological pathways yet to be discovered. Unlocking these secrets could revolutionize human cancer treatment. Whales have cracked part of the code for long life without disease. But for now, their secret drifts beneath the waves, unsolved. Birds, too, hold mysteries beyond our understanding. Every year, they migrate thousands of miles with uncanny precision. Tiny warblers fly from Europe to Africa. Arctic terns circle the globe. Part of their secret seems to lie in Earth's magnetic field, but how they sense it remains uncertain. Some evidence points to tiny magnetite crystals in their bodies, acting as internal compasses. Other research suggests proteins in their eyes might let them see magnetic fields as faint patterns of light. Yet no single theory explains it all. What we do know is that their navigation is astonishingly precise, a natural GPS we barely begin to understand. Even on cloudy days, when the sun and stars are hidden, birds stay on course. Released in unfamiliar lands, they still find their way. It is a sense humans lack, like an invisible layer of reality we cannot perceive. For birds, the world carries directions written into its very fabric, a compass we still don't understand. Monarch butterflies navigate continents with a map we cannot read. Every autumn, fragile monarchs embark on an impossible journey, flying thousands of miles from the northern United States and Canada to a few mountain forests in central Mexico. There, they gather in dense swarms, covering trees in shimmering orange. What makes this migration astonishing is that no single butterfly completes the round trip. The ones returning north in spring are several generations removed from those that left in fall. Yet somehow they arrive at the very same groves year after year. Scientists know monarchs use the sun as a compass, adjusting for the time of day, and they may also sense Earth's magnetic field. Yet no single theory explains it all. What we do know is that their navigation is astonishingly precise, a natural GPS we barely begin to understand. Even on cloudy days, when the sun and stars are hidden, birds stay on course. Released in unfamiliar lands, they still find their way. It is a sense humans lack, like an invisible layer of reality we cannot perceive. For birds, the world carries directions written into its very fabric, a compass we still don't understand. The natural world is full of epic migrations. Salmon hatch in mountain streams, swim to the sea, and years later return to the very stream where they were born. Sea turtles crawl from the ocean onto the same beach where they first hatched. Birds, whales, and insects all traverse vast distances with astonishing accuracy. Scientists have uncovered clues. Some animals use the stars, the sun, or the tilt of Earth's axis. Others may follow magnetic fields or subtle chemical cues. Yet none of these explanations fully account for their precision. How does a bird find the same tree each year? How does a turtle cross an entire ocean to reach one small patch of sand? These journeys remain partly unexplained, guided by senses we do not yet fully understand. Migration is one of life's oldest rhythms, a grand, mysterious dance embedded in the instincts of animals.
Homing pigeons offer a particularly striking example. For centuries, humans have marveled at these birds. Release one hundreds of miles from home, and it rises, circles the sky, and flies straight back to its loft. No map, no guide, just a hidden sense of direction. Researchers propose explanations.
Some believe pigeons use the sun as a compass, adjusting for time. Others suggest they detect Earth's magnetic field like a built-in GPS. Still others point to smell, the idea that pigeons build a scent map of their home region. Yet none fully explain their uncanny accuracy. Even when released in unfamiliar places under cloudy skies, pigeons still find their way home. It is a mystery hidden in their biology, a secret compass we have yet to uncover. For pigeons, the world is filled with invisible cues that guide them across the sky. For us, it remains a puzzle unsolved. No one knows exactly how humans first developed language. Language is what makes us uniquely human. With it, we share ideas, pass down stories, and build civilizations. But its origin remains one of the greatest mysteries of our past. Our closest relatives, chimpanzees and bonobos, can communicate with gestures and sounds, yet none approach the complexity of human speech. At some point, our ancestors made the leap from simple calls to structured language, complete with grammar, abstraction, and infinite possibilities. But when and how did this happen? Some theories suggest language began as hand signals, with words coming later. Others propose rhythmic sounds, chants, or songs, gradually evolving into spoken language. Archaeology offers clues. Carvings and symbolic art, tens of thousands of years old, suggest that the minds that created them were already capable of complex communication. Yet the sounds themselves left no trace. Language allows us to describe what is not present, to plan, to dream, to imagine. It is both a survival tool and a window into thought. Still, the first spark of language, the moment when humans first spoke, remains lost in time. We can only guess at the conversations that began it all. Laughter is universal, but its roots remain a puzzle. Wherever you go in the world, people laugh. The sound crosses cultures, ages, and languages. Babies laugh long before they speak. Groups laugh together, their joy contagious. Yet why we laugh and how it first evolved remains uncertain. Some scientists believe laughter began as a signal of safety. Early humans may have laughed to show others that a threat had passed, turning fear into relief. Others trace it back to primates at play, whose panting sounds during wrestling and chasing resemble laughter's rhythm. But laughter is more than a survival tool. It lowers stress, bonds groups, and releases powerful chemicals that flood the body with calm. Strangely, we laugh not only at jokes, but also at relief, at awkwardness, even at sorrow. Sometimes laughter bursts out when it makes no sense at all. Why should a sound, a breathy burst of air, carry such power? We don't know. What we do know is that laughter is ancient, universal, and mysterious. It is the music of joy shared across all humanity, its roots still hidden in our past. Music moves us deeply, but science can't explain why. A melody can make us cry. A rhythm can make our hearts race. A song can bind us to memories we thought forgotten. Music reaches into the mind in ways words cannot, stirring emotion, shaping thought, and even altering our perception of time. Why certain sequences of sound move us so profoundly remains unknown, yet every culture, past and present, has created it. Music is another language of the human soul, universal and mysterious, a bridge between the seen and the felt, a riddle that has traveled through every corner of our shared history.
Music has no obvious survival function, yet it shapes human life across every culture. Why? We don't know. Some suggest music evolved as a kind of glue, binding early communities through dance and song. Others think it began as courtship, a way to signal vitality and skill. Still others argue it's a byproduct of language and memory, a beautiful accident of evolution. What makes music even stranger is its power. Stroke patients who struggle to speak can still sing. People with dementia recall lyrics when almost everything else has faded. Music can synchronize heartbeats in groups, calm newborns, and stir armies to march. Why should organized sound reach so deeply into our minds and bodies? Science has no clear answer. Music remains one of the most universal, mysterious forces in human life, an invisible thread that ties us together. Love is equally powerful and complex, yet its full nature remains unknown. Love shapes human lives more than almost anything else. It binds parents to children, partners to one another, friends across time. It inspires art, sacrifice, and joy. Biology offers hints. Love floods the brain with dopamine and oxytocin, chemicals tied to reward and bonding. Evolutionary theory suggests it developed to keep parents together long enough to raise vulnerable offspring. But these explanations do not capture the fullness of love, the way it can heal, hurt, and transform us. It can inspire great courage and profound despair. It can make us act against reason, defy logic, and create beauty beyond measure. Love remains at once familiar and unknowable, a human experience that science can describe in part, but never fully explain. Tears are one of humanity's quietest mysteries. They protect our eyes, washing away dust and salt. Yet humans are the only creatures known to shed tears for reasons beyond mere biology. When we are sad, joyful, frustrated, or even overwhelmed with laughter. Why should a drop of salty water carry the weight of our inner life? Tears seem to mirror the mind as much as the body, signaling emotion, connecting us to others, releasing what cannot be spoken. They are both deeply personal and profoundly social, a language of feeling older than words, yet one we cannot fully explain. Tears are one of humanity's quietest mysteries. They protect our eyes, washing away dust and salt. Yet humans are the only creatures known to shed tears for reasons beyond mere biology. When we are sad, joyful, frustrated, or even overwhelmed with laughter. Why should a drop of salty water carry the weight of our inner life? Tears seem to mirror the mind as much as the body, signaling emotion, connecting us to others, releasing what cannot be spoken. They are both deeply personal and profoundly social, a language of feeling older than words, yet one we cannot fully explain. Some suggest human minds are wired for story, and certain themes arise naturally from shared experience: floods, sky gods, tricksters, underworlds, echoing across continents and centuries. Others think myths emerge from common psychological patterns: fear, hope, curiosity, and the need to explain the unknown. Yet, no single explanation suffices. Our instinct to cooperate seems deeply wired, yet mysteriously expansive, reaching far beyond survival and reproduction. It's another window into the strange, unexplained aspects of human nature, our ability to connect, care, and act morally in ways science still struggles to fully account for. Why do we cooperate? Evolutionary theories suggest that working together strengthened early communities, giving them an edge over rivals. Others argue it stems from reciprocal altruism, the idea that helping others increases the chance of being helped in return. Yet humans often go beyond calculation. We volunteer, we share, we make sacrifices, sometimes with no expectation of reward. Studies show even very young children will help others long before they fully understand rules or society. There seems to be something innate, a drive toward cooperation, whose origins remain a mystery. Is it simply a survival mechanism or a deeper moral instinct woven into our minds? The willingness to aid strangers remains one of humanity's most remarkable and enigmatic traits. Civilizations rise and fall,
yet the forces behind their fortunes are still debated. Throughout history, mighty societies, from the Maya to the Indus Valley, Mesopotamia to Rome, have flourished and then collapsed. Why? Some point to climate change, droughts, or natural disasters. Others highlight war, corruption, or the depletion of resources. There are even theories that suggest civilizations follow patterns, cycles of growth and decline that recur regardless of time or place. Perhaps the truth lies in a mix of all these factors, or in something we have yet to understand. What is striking is how sudden the collapse of civilization can be. Great cities are abandoned, knowledge vanishes, and generations fade into silence. Society itself is fragile, and the forces that make it flourish or fail remain only partly understood. We live within a vast and complex network of human endeavor, yet history reminds us that nothing lasts forever, and the reasons why remain mysterious. Human curiosity drives us, yet its origins are still unknown. Why do we wonder? Why do we gaze at the stars and ask questions no other creature seems to ask? Curiosity is a defining human trait, but where it comes from is unclear. Some suggest it is an extension of survival, helping early humans find food, shelter, and safety. Others see it as an evolutionary advantage, pushing us to explore, invent, and imagine. Curiosity, however, reaches far beyond survival. It compels us to study galaxies billions of light years away, decode ancient languages, and pose questions with no immediate answer. Children demonstrate this instinct from the very start, reaching for the unknown and asking endless questions. It seems woven into our nature. Yet why this relentless drive to understand exists remains one of life's great mysteries. Curiosity shapes science, art, and exploration, but the spark behind the question why is still unseen. Storytelling is universal, yet we do not fully understand why we need it. Every culture shares tales around fires, on stages, in books, or on screens. Humans shape words into narratives, carrying heroes and villains, struggles and triumphs. Stories entertain, teach, and inspire. But why are they universal? Some suggest storytelling evolved as a way to pass on knowledge, wrapping lessons in memory. Others see it as a tool to bind communities, giving people shared myths and values. Some propose it allows practice, rehearsing challenges and choices safely within imagination. Yet stories often go further. They conjure worlds that never existed, stir emotions for people who are not real, and linger in our minds for years. No other species does this. Why do humans crave stories, returning to them again and again? We do not know. What we do know is that storytelling is as ancient as language itself, a thread running through every culture, connecting us all. Lightning sometimes forms glowing balls of fire, and we do not know how. Most people are familiar with lightning as a flash in the sky, a jagged streak followed by thunder. But a far stranger phenomenon has baffled observers for centuries: ball lightning. Instead of a quick bolt, it appears as a glowing sphere of light, floating silently, drifting across fields, or even moving through houses. Witnesses describe orbs the size of a grapefruit, glowing orange, white, or blue, sometimes lingering for several seconds before vanishing or exploding with a soft pop. For centuries, ball lightning was dismissed as myth, an optical illusion. Yet in recent years, credible sightings and even a few scientific recordings suggest it is real.
The problem is no one knows what it truly is. Some theories describe plasma trapped by electromagnetic fields. Others imagine vaporized silicon glowing after a strike. Some propose chemical reactions sparked in the air, but no explanation fits every account. The mystery deepens because ball lightning has been seen indoors, even drifting through windows without shattering them. It seems to defy ordinary physics, behaving as both matter and light. Despite thousands of reports, it remains elusive, unpredictable, and unexplained, a ghostly fire in the sky. Similarly, earthquake lights appear in the sky, and their cause remains unknown. During some powerful earthquakes, witnesses report glowing phenomena, flickering blue flames along the ground, flashes like lightning above cities, or strange orbs floating over fault lines have all been observed. These lights have been described for centuries, and modern cameras have even captured them, confirming their reality. Yet why they appear and what exactly produces them continues to baffle scientists. One theory suggests that stressing rocks during an earthquake releases electrical charges, sparking light in the air. Another proposes that tectonic forces ionize gases near the ground, causing them to glow. Yet not every earthquake produces these lights, and their appearances vary wildly. In some cases, they appear before the quake itself, leading to speculation that they might act as a warning system. Their rarity and unpredictability make them difficult to study, leaving earthquake lights among the most eerie natural mysteries, flashes of otherworldly glow in the midst of chaos, reminders that the earth may hold secrets written in fire and stone. Volcanoes are another force of nature shrouded in mystery. Most eruptions are dramatic but manageable: lava flows, ash clouds, small explosions. Yet occasionally a volcano unleashes unimaginable fury, sending enough material into the atmosphere to alter the climate and devastate continents. Scientists know pressure builds as magma rises and gases expand, but the exact tipping point remains uncertain. Some volcanoes lie dormant for centuries, then erupt without warning, while others rumble for years but never explode. The mystery lies in what flips the balance from silence to disaster. Events such as Krakatoa in 1883, Tambora in 1815, and the eruption of Mount Toba 74,000 years ago released energy rivaling that of nuclear weapons. Toba may even have nearly wiped out humanity. Yet modern science still cannot predict which volcanoes will erupt catastrophically or when. We monitor tremors, measure gases, and scan magma chambers, but the inner mechanics of supereruptions remain hidden. Volcanoes are reminders that Earth itself is alive, harboring mysteries we have yet to master. Plate tectonics, too, remains enigmatic. The surface of our planet is in constant motion. Continents drift, mountains rise, oceans open and close, all driven by tectonic plates. Without this restless churning, Earth would lack its landscapes, its earthquakes, its volcanoes, and perhaps even life itself. But why did plate tectonics begin here and not on other planets? Mars and Venus show no active tectonics. Their crusts are locked in place. Somehow, billions of years ago, Earth's crust fractured into giant plates that slide and grind endlessly. Did water lubricate the rocks, weakening them enough to move? Did internal heat reach a delicate balance between rigidity and flow? Or was it triggered by ancient impacts that cracked the crust? We don't know. Computer models offer competing answers, but none fully explain why Earth alone developed this feature. Without plate tectonics, the carbon cycle that regulates climate might fail, leaving the planet barren.
Plate tectonics is what makes Earth dynamic and habitable, yet the reason it began and why it is unique in the solar system remains one of our greatest unsolved puzzles. The origin of Earth's water is equally uncertain. Water covers most of Earth, filling oceans, rivers, and clouds. It is essential to life, and yet its origin remains one of science's great mysteries. Did water arrive on asteroids and comets, delivered during the chaos of the early solar system? Some evidence supports this, as many space rocks contain ice, but the chemical fingerprints of Earth's water do not always match those of comets. Another idea is that water was present from the beginning, trapped deep within Earth's mantle and slowly rising to the surface over eons. Maybe both are true. Some water born here, some brought from space. The balance is still debated. What we do know is that Earth is unusual. Neighboring planets like Venus and Mars are dry, their water lost or locked away. Something about Earth allowed oceans to gather and remain stable. Water is so ordinary that we often overlook its strangeness. Every drop you drink carries the mystery of its origin, a riddle stretching back to the birth of our world. The far side of the moon looks strangely different, and we don't know why. For millennia, humans saw only one face of the moon. The far side remained hidden until spacecraft revealed it in the 20th century, and what we saw was surprising. The near side, the familiar face, is covered with dark maria, vast plains of cooled lava. The far side looks nothing like it, rugged, mountainous, with almost no maria at all. Why should the two faces of the same moon be so different? One idea suggests that the moon once experienced uneven heating, with Earth's gravity baking one side more intensely. Another proposes that an ancient collision reshaped one hemisphere, but not the other. Some theories involve internal dynamics, differences in crust thickness, or volcanic activity, but no explanation fits perfectly. The moon should be symmetrical.
Yet, it isn't simple. The moon's hidden face carries scars and secrets that defy easy explanation. Even now, as spacecraft orbit and landers touch its surface, the far side remains half a stranger to us, a silent witness to billions of years of cosmic history. Beneath our feet, Earth holds mysteries of its own. Deep more than 3,000 kilometers down lies the core, a molten ball of iron and nickel surrounding a solid inner sphere. Its motion generates Earth's magnetic field, shielding us from solar winds and cosmic radiation. Without this protective field, our atmosphere might have been stripped away long ago, leaving Earth barren like Mars. Yet, despite its crucial role, we cannot observe the core directly. Instead, we rely on indirect clues, seismic waves, magnetic records, and computer models. We know the outer core flows like a liquid, powering the geodynamo. But why the field sometimes weakens, wobbles, or even reverses remains uncertain. Mars once had a magnetic field, but lost it. Why has Earth preserved its shield while Mars did not? The beating heart of our planet is hidden, yet its effects touch us daily, in compasses, in auroras, in the very survival of life itself. Earth's magnetic poles do not remain fixed. Every so often, they switch places. North becomes south, south becomes north. These reversals are etched into ancient rocks, a flip-flop pattern stretching back millions of years. The last full reversal occurred around 780,000 years ago. Why they happen is still unknown. Scientists believe turbulence in the liquid outer core can destabilize the field, causing it to collapse and rebuild in the opposite direction. But the triggers remain unclear. Sometimes reversals are rapid, sometimes slow, and sometimes the field merely weakens without fully flipping. The mystery deepens when we consider the consequences. During a reversal, Earth's magnetic field weakens, allowing more radiation from space to reach the surface. What effect this had on early life, or what it might mean for our technological world,
is still largely unknown. Would these mass extinctions have paved the way for new life or merely erased it entirely? The record is incomplete. Fossils tell stories, but they leave gaps. The suddenness of these events, the sheer scale of loss, reminds us that life on Earth is fragile. The causes remain unsettled. Asteroid impacts, supervolcanoes, shifting climates, oceanic upheavals, all may play a part. Sometimes the evidence is clear, as with the asteroid that ended the age of dinosaurs. Other times, multiple disasters overlap, creating cascades of collapse that are difficult to untangle. Even now, as humans study the planet with satellites, sensors, and supercomputers, the forces that shape life on Earth remain partially hidden. Extinctions teach us that stability is temporary, that evolution proceeds amid uncertainty and chance. Life persists, adapts, and rebounds, but only after the planet itself has shifted in ways we do not fully understand. From the magnetic pulses of Earth's core to the rise and fall of ice ages, from sudden mass extinctions to gradual climate change, our planet is alive with mysteries. Every mountain, river, and forest is a testament to processes both violent and subtle, operating on timescales far beyond a human lifetime. Yet for all our knowledge, for all our data and theories, Earth retains secrets. It is a world in motion, a living puzzle, and every discovery seems only to open the door to deeper questions. The story of our planet and of life upon it is still being written in patterns of stone, ice, and water that we are only beginning to read. Why Uranus tilts in this extraordinary way remains unknown. Some scientists suggest a colossal collision early in its history knocked it over. Others propose gravitational nudges from other giant planets shaped its spin. Whatever the cause, the result is a world unlike any other in the solar system, with seasons lasting decades and skies that alternate between eternal light and darkness. Even the familiar planets are full of mysteries. Jupiter's great red spot rages as a storm centuries old, yet we do not fully understand how it has endured for so long. Venus spins backward compared to most planets, its thick clouds hiding a surface hot enough to melt lead. Mercury has ice in its shadowed craters, despite baking in the sun's near proximity. The solar system itself is a collection of puzzles. Saturn's shimmering rings, Uranus's sideways spin, Jupiter's eternal storms, all reminders that even in our cosmic neighborhood, phenomena occur that defy easy explanation. Each planet, moon, and asteroid carries stories we have yet to read, governed by forces both familiar and strange. The universe stretches far beyond our own star. Thousands of exoplanets have been discovered, some rocky, some gaseous, many in the so-called habitable zone, where liquid water could exist. Yet we do not know if any host life, let alone intelligent life. The ingredients are common, but the recipe remains elusive. Even within our own solar system, moons like Europa, Enceladus, and Titan hint at oceans and chemical richness. Life may be there, hidden beneath ice or in alien seas, but we have yet to find it.
Space is full of wonders that challenge understanding. Saturn's fleeting rings, Uranus's sideways spin, and the thousands of exoplanets orbiting distant stars all remind us that the cosmos is alive with mysteries. Every discovery seems to answer a question, yet opens many more, leaving humanity to wonder, what is the nature of the universe, and what secrets remain hidden in plain sight? Beneath her perpetual clouds, Venus hides a landscape of extreme mystery. Temperatures soar above 460 degrees Celsius, hot enough to melt lead, and pressures at the surface are crushing, more than 90 times that of Earth's atmosphere.
Volcanoes, mountains, and vast plains lie shrouded in acid clouds, and radar mapping reveals features that hint at both slow geological changes and cataclysmic events. Some volcanoes may still be active, yet no one knows for sure. Venus's slow backward rotation, combined with its dense, scorching atmosphere, creates winds and weather unlike anything on Earth. Every probe that has landed survived only hours, leaving most of its secrets untouched. Venus remains a world that challenges our understanding of planetary science, a twin to Earth that is familiar in size, yet utterly alien in nature. Neptune's storms remind us that distance from the sun does not mean calm. Winds whip across the planet, lightning may flash in its clouds, and temperatures plunge far below anything we experience on Earth. Its moons, too, hold enigmas. Triton, for example, orbits backward, hinting at a violent capture long ago, and geysers of nitrogen spurt from its icy surface. Neptune remains largely unexplored, a distant world whose secrets tease us from billions of kilometers away. Even a single flyby like Voyager 2 gives only glimpses, leaving the full story of its storms, interior, and history still unread. The origin of these icy visitors lies in a hidden reservoir far beyond Neptune called the Oort cloud. No telescope has ever seen it directly. Its existence is inferred from comet orbits and the dynamics of the solar system. Here, trillions of icy bodies drift in near-perfect stillness, waiting for a gravitational nudge from a passing star or the subtle pull of the galactic tide. Some fall inward, becoming the comets we glimpse streaking across our skies, while others may wander forever in the darkness. The Oort cloud is a frozen frontier, a distant edge of our sun's influence, and its secrets remain completely beyond our reach, reminding us how much of the solar system is still hidden. Many moons hide oceans beneath their icy crusts, but what lies there remains a mystery. Beyond Earth, water is surprisingly common. Moons like Europa, Enceladus, and Titan conceal vast oceans under thick layers of ice. Some may even hold more water than all the seas on Earth combined. These oceans are kept liquid not by sunlight, but by the gravitational pull of their parent planets, which flexes their interiors and generates heat. The possibility of life makes them especially fascinating. On Earth, wherever water exists, life almost always follows. Deep in our oceans, creatures thrive near hydrothermal vents, independent of sunlight. Could similar ecosystems exist beneath alien ice? We have hints. Enceladus jets water into space, rich with organic molecules. Europa's fractured surface hints at dynamic activity below. But until we explore these oceans directly, we can only imagine what forms of life might swim there, simple microbes or something far stranger. Saturn's small moon Enceladus looks like a bright frozen sphere, but NASA's Cassini spacecraft revealed something extraordinary. Geysers erupt from cracks near its south pole, spraying water vapor and ice grains into space. These plumes contain salts, organic molecules, and signs of chemical reactions that on Earth suggest habitability. Beneath the surface, a global ocean lies hidden, kept warm by Saturn's tidal pull. The secrets of Enceladus remained locked beneath ice, waiting for us to discover what stirs in the dark. The geysers on Enceladus may act as vents connecting its hidden ocean to the surface, but what drives these eruptions remains a mystery. Are they powered by hydrothermal vents at the seafloor, similar to those on Earth that teem with life, or do some other unknown processes fuel them? Despite being barely 500 kilometers across, Enceladus has become one of the most promising places to search for life beyond Earth. Its plumes offer a rare, direct glimpse into its secret ocean, but until new missions return, the question of what stirs beneath its ice remains unanswered. Titan, Saturn's largest moon, presents a different puzzle. This world has rivers, lakes, and seas, but they are made not of water, but of liquid methane and ethane. Its hazy skies and alien weather sculpt landscapes utterly unlike Earth's. The mystery lies in its methane. Sunlight should break down methane over time, yet its seas persist. Something hidden underground or woven into its chemistry must be replenishing them. Cryovolcanoes may release methane from the interior, or chemical processes we do not yet understand could be at work. Intriguingly, methane is also considered a potential biosignature, a hint that life might exist in forms very different from our own. Could Titan's methane be biological in origin? We don't know. Its methane cycle mirrors Earth's water cycle in uncanny ways, yet its hidden source that keeps its seas full remains a mystery waiting to be solved. Mars, too, holds secrets of a watery past. Billions of years ago, rivers carved valleys, deltas formed, and lake beds mark where water once flowed. The planet may even have held oceans. Today, Mars is dry and frozen, with only thin wisps of water vapor in the atmosphere. Where did it all go? Some water may be trapped as ice beneath the surface, some locked in minerals, and much may have escaped into space after Mars lost its magnetic shield. But the full story remains unclear. Did the water vanish slowly or in sudden bursts? Could liquid water still flow underground today, hidden from our view? Understanding Mars's rivers could reveal whether the planet once hosted life and whether it might still be possible.